What we learned on Thursday is, in the most general sense I can put this, is that when you have a function, y equals f of x, and f of x can be anything. We focused in the lesson on linear functions and quadratic functions, but they don't have to be linear functions or quadratic functions. They can be any function at all. It's just that in grade 10 you study linear functions and in grade 11 you study quadratic. But if you have a function that looks like this is y equals f of x. And what I'm about to explain to you by way of review is so crucial to what we do today. Then I ask you to sketch y is equal to the absolute value of f of x. This is the reasoning that goes into what is about to happen. When you look at the original function in brown, f of x is y. F of x is the y coordinate. So when we say what is the absolute value of f of x, we're saying, this gets a little tricky, that the new y coordinate is the absolute value of the old y coordinate. That's what's going on here. So any place the old y coordinate was 0 or positive, the absolute value of that will still be the same thing. So this has a y coordinate of 0 on the original graph. This has a y coordinate of 0. So does this. So does this. And the y coordinate on the original graph is positive. Everywhere in these regions. So the absolute value of the function, a little wobbly there, but that's okay, will contain this piece, which doesn't change, and this other piece is going to flip upside down. So this part, and I'm just going to pull it off here so you can see this, this part, which does not include those x coordinates, is negative. To make it positive, so this is all negative down here. It's all negative here. To make it positive, you have to flip this up. So that green one is the absolute value of the function. That's what it really boils down to. And if you know that, you can answer any questions about intercepts or domain or range or any of that. Take a minute, please, and look over your work from page 375. And does anybody have any questions at all you would like me to go over? You sure? Give you another minute. Although it looks like you're pretty well decided. No questions? All right, let's move on then. We're looking today at absolute value functions part 2. And we have one goal today. And I hope I've done a good job of setting the stage for this. But we'll see. The goal is to take an absolute value function and write the absolute value function without absolute value symbols. So that if I give you an absolute value function like this one, too easy, like this one, If we're going to rewrite it with absolute value signs, then if I put this into your graphing calculator and I put our answer into the graphing calculator, we get the exact same thing. But we don't use absolute value signs. Okay? And when we do that, we are writing it as what's called a piecewise function. So to begin with here, let me just tell you that a piecewise function is a function that has different pieces to it. In other words, if I tell you the answer to example, it doesn't matter, 1c, and you're going to enter it into your graphing calculator to graph the answer, which will be a piecewise function, you're going to have to graph two functions because it's going to be two pieces. You're going to have to graph y1 for one part of this and y2 for the other part of it. Okay, let's get to the official notes here. Recall that the absolute value of a negative quantity is the negative of the quantity. Just let that simmer around a bit in your head. The absolute value of something that's negative is the negative of that thing. So, for example, the absolute value of -3 we know is 3, but it's 3 because it's negative of -3. We talked about this, I've talked about it ever since we've introduced absolute value to you, that if the thing inside the absolute value is negative, we have to make it positive when we remove the absolute value signs. What's one way to make something that's negative positive? Take that negative thing and multiply by -1. So all this is saying is, and I've written this a number of times, if x is negative, then the absolute value of x equals -x. And you really have to think carefully about that. If x is negative, then the absolute value of it is -x because it's negative of a negative, which will make it positive. We're going to use this idea to write absolute value functions as separate functions without absolute value symbols. And as I've already said, that's called a piecewise function. So we're going to write the piecewise function. I think we have about 5 or 6 of these to do today. We're going to write the piecewise function for each of the following, and we're going to sketch the graph. F of x equals the absolute value of x. So here's how we're going to do it. We're going to split that function into two pieces. One of the pieces will have to be x without the absolute value signs. And that is going to occur wherever x was greater than or equal to 0. So I need to put a comma here. And I would like everybody to focus on this statement right here. X is greater than or equal to 0. Okay. If x, which is what's in the absolute value signs, is greater than or equal to 0, do you need the absolute value signs? No. So that's why we drop them. On the other hand, if x is negative, then we can drop the absolute value signs, but we have to multiply what was inside by -1. And this is not really that tricky. Well, I shouldn't say that. In practice, it's very easy to break this apart. But it is tricky in terms of understanding this. Let's just finish this off by putting one of these curly sets of brackets. That's what f of x is. Now, what does this mean? It means this, that if we had a number line where 0 is right here, then whenever x is equal to that number, or greater than that number, f of x is x. But whenever x is less than that number, f of x is negative x. So think of it this way. You have a different rule for calculating the y-coordinate depending on where the x-coordinate is. So, for example, if I take a look at x equals 0, then I use the rule that I've written in red. The y-coordinate is 0. If I look at, I'll even do it this way. If I have x equals 0, then the y-coordinate is 0. If I have x equals 1, the y-coordinate is 1 because 1 is a number greater than or equal to 0, so I use the red rule. If I have a 2, then y equals 2. I use the red rule. So as long as I'm to the right of the origin, I'm going to get a whole bunch of dots that line up here. What about if x was negative 1? Well, negative 1 is a number less than 0, which means the y-coordinate, f of x, is negative 1 times the x-coordinate. Negative 1 times negative 1 gives you 1. Without this negative in front of the x here in green, all of these points would line up like that. But because they're to the left of 0, I need to multiply those y-coordinates by negative 1. And it's at this point in time that some of you will be saying, this is really no different than what we did yesterday. If it's below the x-axis, we flip it up. The difference is what's written in the top right corner of the screen. That's how we write the function. So all of these have x-coordinates that are less than 0. We multiply them by negative 1 to make them greater than 0. So these points are going to be here. And we should be familiar, I'm not going to use all the colors now, we should be familiar with the fact that this is the absolute value of x. I want to show something to you now. And not all of you will necessarily pick up on this, but some of you might be interested in it. I'm going to graph y equals x. Okay. Zoom 6. Now, is part of our function y equals x? Look at the two pieces. Is one of the pieces y equals x? Yeah, the top piece. But it's only valid when x is greater than or equal to 0. So I'm going to show you how you can tell your calculator to only graph it if x is greater than or equal to 0. Okay? So you are going to go into y equals, and you don't need to know this, but I think it's interesting, and we're going to divide by something. And what we're going to divide by, it's going to seem weird, is that inequality. X is greater than or equal to 0. I know this seems strange. I'm going to go divided by bracket, and then I'm going to put x, and then I'm going to put greater than or equal to 0. And I can get the greater than or equal to by going to, and I was just trying to remember where it is. I believe it's under the test menu. Yep. Now, I want to explain to you what's going to happen here. And this is more of a computer programming language kind of thing. In the machine language that your calculator uses, any true statement is assigned a number of 1 and any false statement is assigned a number of 0. So if this statement is true, your calculator will graph y equals x over 1, which is x. So when your calculator makes a table of values, it's going to try x equals 1, x equals 2, x equals 3, x equals 4, and all of those numbers will be true for x is greater than or equal to 0, so it will assign a 1 there and it will divide by 1. But if my calculator, and I will demonstrate this to you, if my calculator makes a table of values and uses x equals -5, -5 makes this statement false, so your calculator is going to attempt to graph x over 0. And it can't. And I can even show this to you by going to the table. I'll set up my table to start at -5 and go up by 1. Can't graph anything. So remember what it looked like a minute ago. It was a straight line. Now look at what it looks like. And there was a little pause there where my calculator was trying to plot points, but it couldn't. And then I'm going to pull this off. Actually, what I'm going to do instead, and we won't do this with all of my calculator or all of my examples, but let's go open. Let's open another 83. So on this calculator, I'm going to graph -x. And of course, we know what that looks like. That's a line with a slope of -1. But I want to graph it only when x is greater or less than 0. So I'm going to divide by, in brackets, x, go to my test menu, is less than 0. I don't know who came up with this. It's pretty cool. And boom, it stops there because it can't calculate anything else. And if I take these two and lay them on top of each other, that's a happy medium, I get that function. Let's try another one. Y equals the absolute value of 2x minus 4. So now I'm going to kind of teach you the nuts and bolts of how to just get an answer, kind of. We know that this is going to split into two functions. One, where the absolute value is not needed. And I'm going to actually write that here. Why is the absolute value not needed there? Because that thing was already greater than or equal to 0. And one, where we have to multiply that thing by -1 because the absolute value is needed. Now, why would the absolute value not be needed? This is going to get a little messy in your notes. And I don't know that you want to write this down. The absolute value is not needed because 2x minus 4 is greater than or equal to 0. The thing in the absolute value signs is already positive, or 0. Why would it be needed? Because 2x minus 4 is less than 0. And before we go on, I know that some of you can overthink this. The equals to goes with the part that's not needed. It's not wrong if you do it the other way, but I would prefer that you put the equals with the greater than. Okay. But, we don't want to write this. Don't do this. Again, it's not wrong, but it's not good enough. What I want is, what is x? What's the domain for x where you don't need the absolute value signs? And all we do is you solve this inequality for x. That's it. If you want to know where 2x minus 4 is greater than or equal to 0, then add 4 to both sides, divide both sides by 2, and you get x is greater than or equal to 2. And this would, of course, have to be x is less than 2. Where the one function stops working and the other one takes over is the same place. The bottom function is used all the way from negative infinity up to just before you hit 2, and then when you hit 2, the other one takes over. So they have to match up. So the graphing part isn't as important, but let me run through graphing it. Don't draw anything just yet. You should know that this is a line with a y-intercept of -4 and a slope of 2 from grade 10. So if the y-intercept is -4 and the slope is 2, don't draw this yet, then this function looks like that, right? Except it's only good when x is greater than or equal to 2. That part doesn't exist. So when we sketch this, that line is only good starting at 2, which kind of makes sense because that line is only positive starting where x equals 2. If you were to graph this, which is -2x plus 4, that's a line with a y-intercept of 4 and a slope of -2, but it's only good before 2. And again, the graph is not that big of a deal. But I think the purpose of the graph is to help you connect your understanding, to help clarify your understanding of what we've got written on the left-hand side. Before we go on, I want to add one more layer to this, and I'm going to do it in a general way. If you have y equals the absolute value of f of x, you break it into f of x and negative f of x. This is where f of x is above the x-axis. It's actually where it's on or above the x-axis. Because if it's on or above the x-axis, then based on what we did last week, you don't need the absolute value signs. You leave it alone. This is always going to be where f of x is below the x-axis. So let me go back to the previous example and just say, what if we had to take y equals the absolute value of, I'm sorry, was that it? Okay, and we're going to break it apart. All I'm saying is one of these will be 2x minus 4. One of these will be negative 2x plus 4. Just give a little bit of thought as to where I got negative 2x plus 4 from. I'm multiplying 2x minus 4 by negative 1. So what you could do, and I don't think I would ever give this to you as a written response. So you could always use your graphing calculator and say, I'm going to graph 2x minus 4, and I'm going to see where is it on or above the x-axis and where is it below. I hope that everybody understands you can only answer where is it above or on and where is it below by finding the x-intercept. It's 2. you can see that when x is 2 or greater than 2, the function is above the x-axis. And you can see, looking at the graph, that wherever x is less than 2, it's below the x-axis. That's what you're going to do every single time. Let's try C. Absolute value of 1/2 x plus 1. Heck, you know what? Let's try this with our graphing calculator. But not by graphing the absolute value. We're going to graph 1/2 x plus 1. Well, before we do that, let's lay out the groundwork. If I multiply that by -1, I have to multiply both terms by -1. So now we need to find out where is y rather, where's the function above or on the x-axis. So we're graphing y equals 0.5 x plus 1. 0.5 is 1/2. All I care about is where it crosses the x-axis. That's it. So I'll just expand this a little bit for us. Let me close that one off. All I care about is what this point is. Now, I don't know. I would not recommend just looking at it and guessing. We know we can find it by using the 0 function in our calculate menu, going to the left, then going to the right, -2. See, it doesn't really look like -2 to me, so it's a good thing I checked. This is at -2. So look at this graph visually. Where's the graph horizontally? Where's the graph above the x-axis? When x is greater than -2. Where is it on the x-axis? When x equals -2. So this point, I know I'm repeating myself, but this point does not require the absolute value because that point has a y coordinate of 0. The absolute value of 0 is just 0. None of these points require the absolute value. So what does that mean? It means when x is greater than or equal to -2, leave it alone. That must mean x is less than -2 for the other half, and we're done. And again, I don't care if you graph it. The graph might help you understand where that tipping point is by locating an x-intercept. The graph, by the way, would look like this. Because that part that's below gets folded up. But that's really last lesson. Are there just 2 more? Do I only go to E? Okay. The next 2, I believe, are quadratic. So x squared minus 5. Okay. Well, I did say I wouldn't give this to you as a written response, but we are expected to know how to do algebra. Let me repeat myself again. You need to know the x-intercepts to find out where it's above and where it's below. So x-intercepts of this function will tell us how to split up that absolute value function. X-intercepts are found by setting y equal to 0. So 0 is equal to x squared minus 5, which means 5 equals x squared. And that means x equals plus or minus root 5. I guess we'd better calculate an approximate value of root 5. I'm guessing it's around 2.2. Allie, how did I do? 2.36. 2.36. Let's call it 2.4 then. So, yeah, 2.236? Okay, so 2.2 to the nearest tenth then? Okay. So that is about, now be very careful about what I'm drawing here. What I am actually going to draw is this, just for now. We know that this has x-intercepts of negative root 5 and positive root 5. And we know that since it's positive x squared, this is a parabola that opens up. Okay? We also know the y-intercept is negative 5 because the y-intercept is always the constant term. So this graph looks like this. Yeah, a little shaky, too much, or maybe not enough coffee today for me. But that's neither here nor there. Would you agree that's a not bad representation of that graph? Okay. So where are the absolute value signs needed? Well, they're needed for anything that's below the x-axis. So when we write this out, one part will be x squared minus 5. The other will be negative x squared plus 5. Now, we'll do the bottom piece first, the negative x squared plus 5. Where is that needed? It's needed in between these two numbers, because in between those two values of x, the graph is negative. So we need to multiply the function by negative 1 to flip it up. So we can put negative root 5 is less than x, which is less than root 5. That's the green part that I've put on there. That green line with the two empty dots is not part of the graph. I'm just indicating a domain. Where is the absolute value not needed? On these points and to the left and the right of them, because for those domains of x, the thing is above the x-axis. So how do we write these? This is x is less than or equal to negative root 5. This is x is greater than or equal to root 5. Of course, this is negative root 5 is less than x, which is less than root 5. I'm trying to give you different ways to visualize what the math is saying. So those green and red lines are just showing different domains that the two pieces of the function work in. So this one is x is less than or equal to negative root 5, x is greater than or equal to positive root 5. We still, and maybe this is worth noting, even though there's three pieces, we still only write two. Right? The function and the negative of the function. I know from experience that what's going to happen for some of you is, and we have one more example to do, is you follow this along and it makes perfect sense and you're nodding your head and I can see that you understand. And then it's going to happen with this and another thing in this unit. And then you go to do it on your own and at some point you go, what am I doing? Like it's like a wisp of smoke disappears. It's gone. So it's very, very slippery. Negative x squared plus 2x plus 6. Why don't we use our calculator to find out the x-intercepts and what this thing looks like? So we're going to be graphing this on our calculator to find out where we can just plot negative 1/2 x squared plus 2x plus 6, and where we can plot 1/2 x squared minus 2x minus 6. And again, I hope everybody's okay with how I'm changing it. I'm multiplying the whole thing by negative. See, could we do all the algebra to analyze this function based on everything we know from Unit 3? Yeah, we could. We could complete the square, find the vertex. We could use the quadratic formula to find the x-intercepts. But I feel as though even though it's only Monday, it's been a long day. So let's cut ourselves a little bit of a slack here. Negative 0.5x squared plus 2x plus 6. Zoom 6 because why not? It's looking like it's crossing at negative 2 and 6. I'm going to give everybody a minute to confirm that it's crossing at negative 2 and 6. And if you suspect it is, I think the quickest way to check is to go to your table. I mean, you could find the zeros by going to your calculate menu, but you could just look in your table as well. I just want to check something here. Is your grid the same as mine on your handout? Is it show more? Shows less. What does it go up to?
For them, negative x and y, it just goes up to negative, or it's just up to negative 4.
Does it go up to more vertically?
Yeah, it does.
Okay. Well, as my dad would tell me, if you're going to do something, let's do it right. So this will only take a second for me to get out I guess I captured the wrong image. I'll get the right one right now. This is the final example, am I correct? Oh yeah, totally different. There we go. This is the one, Lucas? Okay, thank you. By the way, in all that time, you have confirmed that it crosses the x-axis at negative 2 and 6. It crosses the y-axis at 6. Very roughly, I just want to check something quickly here. I think it maxes out at 7. And it does so here. You don't need to get all of this detail. I just decided to do so. There's a rough approximation of it. Not too great. That might be a little bit better. So we said, let me rewrite this because I had to recapture the image, that f of x was equal to negative 1/2 x squared plus 2x plus 6. Is my memory correct? Okay. Where is it equal to that? It's equal to that here, here, and everywhere in between. Because everywhere in between, it's above the x-axis, and at those points, it's on the x-axis. And if it's on the x-axis or above the x-axis, you don't need the absolute value signs. So what we can put for that piece is negative 2 is less than x, which is less than 6. And then 1/2 x squared minus 2x minus 6. We just put everything else, which would be here. X is less than negative 2 and x is greater than 2. just a final note here, just to make sure. You see on the green line I drew on the left, I drew up and to the left, and on the one on the right I just drew to the right. There's no difference. It's just my brain just took over there. So ultimately what it boils down to is, as I've said, the absolute value of f of x can be written as f of x and negative f of x, but you need to put here what are called subdomains of x. You need to figure out somehow what's the domain. I always want to say range of x values. That would be wrong. What's the domain of x values that each one can be used for? And the absolute value signs are not needed if the graph is on or above the x-axis. They are needed if it's below the x-axis. That's it for today. Tomorrow and the day after we'll be looking at solving absolute value equations, which uses the same kind of idea. Your assignment is on page 377. You also have the assignment number 4, which I had changed the due date to tomorrow, I believe, correct? Okay, so you can polish that up. Shannon, I don't know if I sent yours to you. Did I? I did. Okay. So get to work on that, please, and I will come around now. We'll help you out. You want to hand it in now? Okay. Yellow folder if you're going to turn it in now. Yeah. An exam this week? No. This is a monster unit.